Hello and welcome back. We now look at a very special setup of neural networks, the autoencoder. The left part here shows a typical autoencoder architecture. We have an input given by x, and we have an output, and here we denote it not by y hat for a prediction, but x hat. Now why is that? Essentially, the network architecture learns a mapping between the input and itself. So for example, if we were to feed in images, we would learn how to reconstruct the same image. However, you notice here the key that there is this intermediate layer Z. So how do we do this, and what is the role of the layer Z? We force our mapping to go through this intermediate state, and this may be smaller in dimensionality than the input and the output. So essentially we would force our input images in this example through a little bottleneck, and we want to learn how to create from this bottleneck the same images again. So for example, we can use this to reduce the dimensionality. But essentially what we do is we create what's called a latent space representation of the essential characteristics of X. So when you remember, we had an image, for example, in the input layer, and we were reconstructing the same image in the output layer. But now we use this small bottleneck Z. So for the network to be able to do this, the encoder part towards that needs to learn what makes these images characteristic, and this is the latent space representation of these images. And then the decoder reconstructs this latent space and gives us back the original images. We can of course have many more layers in the encoder and decoder setup. So what are typical applications for this? When we focus on the encoder part, we want to reduce the dimensionality, or for example, we want to generate features. As we just said, the encoder creates a latent space, and then we can use this latent space as, shall we say, an abstract representation of all the images that we have learned. We can also apply only the decoder part, and then we can use this, say, for sample generation according to Z. For example, then if we vary this latent space, we could see what this corresponds to in the real space. We can also use both of them together. For example, we can apply this for denoising images. Instead of learning the identity, we give it noisy input. So when we train this autoencoder, we would give the clean images always for the output part, but we would give noisy images to the input part. And so essentially the combination of encoder-decoder learns not only the identity mapping, but what is noise in these images. We can also use this for outlier or anomaly detection. We train on normal data, and then the anomaly in these data will have a large reconstruction error. For example, when we assemble components, we can use this for assembly verification by comparing what the expected identity would look like and what the actual object we have assembled looked like. And if the reconstruction error is very large, that is a good indication if we have not assembled everything correctly. A variation of this is called variation autoencoders. In standard autoencoders we have the latent space representation, but this may not be continuous. So this is good for distinct classes and anomaly detection, but it may be difficult for continuous cases, and this is what the variation autoencoder does. Instead, we learn the parameters of some probability distribution, for example a Gaussian or normal distribution, and then the decoder learns to make a random sample out of this. So essentially in the standard autoencoder here on the top we have the encoder goes to the intermediate state Z, this is our latent space, to the decoder, and now we split this up and say we have a continuous probability distribution, and our Z is essentially comprised of the parameters of this distribution. So this is also what's called the reparameterization trick. Because the issue with the variation autoencoder is that it involves now sampling from this random distribution, and this leads to a stochastic behavior. Unfortunately, the stochastic behavior doesn't work with backpropagation, so we need to think about training this. And this is where the reparameterization trick comes in. We split the learnable parameters, mu and sigma, for example, for the Gaussian distribution, and separate this from the noise. So the noise will not be learnable, it's always a standard Gaussian, but what we want to do is, instead of sampling from this, we sample from this noise and shift it by the mean and sigma. So essentially, this reparameterization trick makes it more accessible for our network to separate the parameter that we need to learn from the noise.